Hello students, this is the second video in the probability review series. I'm going to be talking about the second half of the packet that I gave out, and I will hope to answer all your questions about tree diagrams. The next page that we're going to be focusing on is page number 7, in which it asks us to draw a tree diagram to show sample space. First, it talks about red, green, or blue chips being selected. That's the first event, we call that. And coin is tossed. That's the second event. A tree diagram is a diagram that represents all the different possible outcomes from multiple events. I'm going to show you on the next page what my tree diagram looks like. And here's how it's set up. It starts from one central point, and the first event can be described as having 3 different outcomes. Remember, in the problem it said it was either red, blue, or green chip. The second event is a coin being tossed, and the 2 outcomes for coins being tossed are heads and tails. Notice that from this point, whether there was a red chip being drawn, for example, it's still possible that the coin flip ends up either heads or tails. If there was a blue chip being drawn, heads or tails. If there was a green chip drawn, heads or tails. So the color of the chip does not affect the side of the coin that it lands on. Those are called independent events. Now, at the end here, where it says outcomes, this list is called the sample space. It's called the sample space because it lists out all the possible outcomes of 2 different events or multiple different events. Going back to the problem here, I can see that it asks me to find probabilities from the tree diagram. I'm going to take a little mini copy of the tree diagram and paste it here so that we can use it in our calculations. And there it is, our little mini copy. We're going to use the tree diagram to find each probability. The probabilities of all of these events are based on the sample space from our tree diagram. So, for example, there are 1, 2, 3, 4, 5, 6 different outcomes that are possible. And the first outcome is having a red chip and heads come up on the coin. The second outcome is red chip and tails coming up on the coin, and so on. Each of these outcomes are different separate outcomes, and they each have a probability of 1/6 because they're all equally likely. The chips are all equally likely to be drawn, and the heads and tails are both equally likely to be landed on. We'll talk about different likelihoods later. This is just a very basic probability review. So if we look at the problem, the first problem talks about the probability of green and heads on the coin. Well, we can see that there's only one outcome. Pardon me, that's the wrong circle. We can see there's only one outcome that talks about a green chip and landing on heads. All these other outcomes either have heads and a different color or green and a different side. So the probability of getting a green chip and heads is 1 out of these 6 different possibilities. You'll notice that this process is very similar to the other processes we went through where we listed out all the numbers and we circled out the desired outcomes. It's the same exact deal. So I know that green and heads is going to be the probability 1 out of 6. So we'll write that in, 1 out of 6. I want you to try to use the tree diagram to calculate the other probabilities. So pause the video and I will come back with the answers in a moment. Alright, here are your answers. You'll notice that for question number 3, it says blue and heads. Well, there's only one outcome that is blue and heads, so that's why we selected that. For 4, we actually simplified it. It said green, heads, or tails. Well, we know the probability of getting green is down here. And heads or tails, both of those are desired outcomes. So I can circle green heads and green tails. That's 2 possible outcomes, desired outcomes rather, out of a possible 6. The probability of getting blue chip and heads on the coin is 1 out of 6 because there's only one outcome that's listed there. The probability of yellow and tails, well, there's no yellow out of all of these different possible outcomes. So I would say that the probability there is 0. And then finally, the probability of not red and then heads, well, we can't use any of these outcomes because they're both red. We can use this outcome because it's blue, which is not red, and heads. And we can use this outcome because it's green, not red, and heads. So 2 out of 6, again, that's 1 out of 3. Moving on to the next problem, it talks about the Cabrillo family consisting of a father, mother, grandmother, daughter, and son, 5 people. On a trip, 2 members of the family sit in the front seat. One is adult and one is a child. Make a tree diagram to show the sample space of the occupants of the front seat. I want you to get a little bit of experience making tree diagrams, so pause the video now, try to draw it on your paper, and then I'll come back with the correct answer. Alright, let's take a look at the answer to this question. For question number 8, it talks about the family consisting of 3 different adults and 2 children, so I separated those people into adults and children. And then it asks us to make a tree diagram to show the sample space. Again, sample space is the total different outcomes that can happen for a problem. Scrolling down here, I'm going to show you my tree diagram. There are 2 different events that are happening, and we call them events because they're situations with different outcomes. The first event is going to be an adult in the front seat, and you can see that there are 3 different outcomes for that event. It could be a father in the front seat, mother in the front seat, or grandmother in the front seat. And then after that, there is a second event. After you choose the adult in the front, of course you must choose the child. So it's either the daughter or the son. Then, last but not least, our sample space is all of these different lists. And that stands for father-daughter, father-son, mother-daughter, mother-son, grandmother-daughter, and grandmother-son. We're going to move these over here into what's called sample space, but understand that at the end of this stalk, at the end of this leaf, I guess you could say, in the tree diagram, that corresponds to father and daughter. This leaf corresponds to mother and son, etc. Now, it asks us to use the tree diagram to find each probability. Now that you have this tree diagram, let's see if I can put them all on the same screen. I can't, unfortunately. I'll make a small copy of it and I'll put it down here. What I want you guys to do is try to figure out the probabilities of each different event here, of father and daughter, one occupant, etc. So pause the video now, and I will unpause the video in a moment. Alright, as you can see, I made a smaller copy of the tree diagram here, and I'm using it to find each probability. Let's take a look at some of the more complicated ones. We see that for number 12, it says son and daughter, the probability is 0 out of 6. That means that none of these outcomes include both a son and a daughter, which makes sense because in the front seat, it has to be one older person, one adult, and one younger person, one child. So there should be only one child in the seat, and there are 2 children here, so the probability is 0 out of 6. One occupant being the daughter is 3 out of 6, which is because this outcome has a daughter. That's 1. That's another daughter, 2, and another daughter, 3. So that means it should be 3 out of 6, or 1 out of 2. And remember, we're expressing our probabilities as fractions in simplest form. The probability of both females is 2 out of 6 because we have mother-daughter here and grandmother-daughter, both females, so that should be 2 out of 6, or 1/3. For female and male, I was careful to include situations where the first choice was also a male and the second choice was a female. This is saying the probability that one of the people is female and the one of the people is male or identifies as male. So the father-daughter counts as female-male, mother-son is female-male, and grandmother-son is female-male. So that's 3 out of 6. Everything else should be fairly self-explanatory. Alright, let's move on to the next page. In this situation, there are 3 different events that happen. It says 3 coins are tossed. And it asks us to make a tree diagram to show the sample space, then find each probability. I'll allow you to try to draw this sample space, keeping in mind that there are 3 different events, not 2 as the previous tree diagrams have suggested, and then we'll try to find the probabilities. So draw the tree diagram now. Alright, and you see the tree diagram here. You may notice that the font in this tree diagram is slightly different than my font. I'm thankful to the folks on onlinemathlearning.com for this picture. I borrowed it from them. It asks us to make a tree diagram, which we did. Now we're going to find probabilities. The probabilities here are going to be dictated by the outcomes or the sample space here. Pause the video, try to answer 5 through 8, and then I will show you the correct answers. I'm actually going to show you one example of this tree diagram being used to find probability because it's a little different than the previous tree diagrams. I'm giving the answer to number 5 as 3 out of 8 because it's asking for the probability of exactly 1 tail. If I look at my outcomes, I can see that this outcome has exactly 1 tail, so does this, and so does this. There are 3 different outcomes with exactly 1 tail. This has 2, for example, this has all 3, this has no tails, but these 3 outcomes have 1 tail. So I'm saying 3 is my desired outcomes. The reason I'm using 8 as my possible outcomes is because there are 1, 2, 3, 4, 5, 6, 7, 8 different outcomes. So my possible outcomes, my denominator is going to be 8 in this case. Anytime you have a new tree diagram, it's going to have a new possible outcomes number based on the number of outcomes that are possible, based on the number of branches on the tree diagram. Alright, pause the video and try to find the answers to 6, 7, and 8. Alright, here are the correct answers. I want to take a look at numbers 7 and 8 because they're a little bit more complex than the previous ones. Number 7 says the probability of at least one head. Well, that means that there's got to be either one H in the outcomes, two H's in the outcomes, or three H's in the outcomes. So this matches the bill because there's at least one H there. So 1, 2, because there's at least one H, 3, 4, 5, 6, because even though there's one H, that's at least one, 7, at least one H. This is the only outcome that has no heads at all. So we can say that 7 of the 8 outcomes have at least one head. Same thing with number 8. It says probability at most 2 tails. So there could be 2 tails, or maybe 1 tail, or maybe 0 tails. So this counts. So does this, so does this, so does this, so does this, this, but this doesn't because this has 3 tails, and that's not at most 2 tails. So we can still say it's a 7 out of 8. For numbers 9 through 18, they're using a different tree diagram. I'll let you pause the video, draw that tree diagram, and try to determine the sample space, and then we'll take it from there. Alright, here's the tree diagram. Again, online mathlearning.com was very helpful in providing this tree diagram. One small note about this, if I'm using what's called a number cube, you call multiple of them dice, so the plural of number cubes is dice, but if you're using one singular, this should actually say die, not dice. So that's one nitpick I have on that particular site. But naming notwithstanding, this is a perfect example of a tree diagram for heads and tails for a coin, and dice being, or a die having 6 different faces. Now we can use the tree diagram's sample space here to find all of the different probabilities in 9 through 18. So pause the video now, take a while to try to figure out those probabilities, and you can check your answers in a moment. Alright, check your answers. You can see a couple of odd ones. Take number 12, for example, the probability of getting tails or heads. Well, all of the different possible outcomes, all 12 of them have either heads or tails. It has to be because the coin doesn't really land on anything else other than heads or tails. So all 12 of the outcomes are our desired outcomes. There are 12 possible outcomes, which gives us 1. If you remember at the graphic from the beginning of this video, it shows probability being a number in between 0 and 1. 1 is our certain likelihood. 1 is our certain probability. So it is certain that when I perform this experiment, I'm going to get all 12 of the different outcomes being either tails or heads. You can also see, for example, that a number is less than 4. Well, in this case, numbers that are less than 4 are 3, 2, and 1. So I have 6 different outcomes with a number that is less than 4. So 6 divided by 12 is 1 out of 2. Now, this spiral review down here is review from other math classes. It is not necessary for you to know the answers to these questions, except for question number 19. If you were to solve this proportion, you would get v is equal to 30. We can leave all the rest of these alone. Take a look at the next page. On the next page, it talks about independent events, which, as you recall from the previous video, are events that do not affect each other's outcomes. So, in other words, an independent event is an event that does not affect other outcomes. For the practice problems, it asks you to indicate whether the events are independent or dependent. Pause the video, and I will give you the answers in a moment. Alright, in these practice problems, you can see that most of them are going to be independent because the events do not alter the other events. Or in other words, the outcomes are not affected by the other outcomes. The only dependent event is question number 6. You can tell that you wanted 2 different flavors. So if you choose one flavor, let's say you choose vanilla, the next choice, the next event, the choice is going to be different because you are not able to choose the same amount of flavors. You can only choose 30 flavors. But everything else, it should be independent events. We're going to be talking a lot about dependent and independent events and answering these questions in class, but for right now, make sure you're able to tell the difference between independent events in which the outcomes do not affect each other and dependent events in which the outcomes do affect each other. Good luck studying.